All right, welcome to Chapter 3, Section 3. This is a long section, so we're going to break it up into three different podcasts. A lot of stuff is pretty um, kind of tough to visualize, and so we're just going to continue on with our model of the atom. Now, when we were done with our last podcast, we had this model of the atom, Rutherford's, a nucleus surrounded by electrons. And Rutherford felt that electrons were traveling around the nucleus like planets. And that was kind of the belief. But what happened is that scientists were trying to understand, well, if the nucleus is positive and electrons are negative, well, then how come this positive thing right here isn't attracting this negative thing as it goes around? So as it goes around, why is it not spiraling in to the nucleus? So that was kind of a problem with the Rutherford model. So about 2 years later, a physicist by the name of Niels Bohr came along and developed a model that was based on the amount of energy that electrons have. So here you can imagine this dot as the nucleus. That little bitty circle would be the level where an electron resides. Here's this circle right here. Here's another one where an electron resides. And this third energy level is where more electrons reside. So we've got energy level 1, energy level 2, energy level 3. Now what was very interesting about Bohr's model is the idea that electrons can't go slowly, or I guess gradiently, from one energy level to another. The idea was that they jump from this one to this one. Almost like if you were to walk, oops, let me try and draw a little better ladder. Like if you were going to go upstairs up a ladder, you wouldn't go in between the rungs. You would go from one rung right to the next rung. Okay, almost like, since I'm a Star Trek fan, teleporting from one level right to the next. These discrete energy levels, and that was the basis of his idea. So let me move on to the next slide here. So here's his model. The idea is that electrons are traveling from one energy level to another. Now don't get confused by this equation right here. You don't have to worry about that. We are going to deal with that later. But this talks about what happens with the energy when an electron goes from this one to this one. But right now we're talking about an electron going from energy level 1 to energy level 2, or energy level 2 to energy level 3, or ever energy level 1 to energy level 3. They're jumping instantly. All right. And so that was the idea of Bohr's model, which is more or less held to be true today. But there were a few issues. First, another physicist by the name of Louis de Broglie, noticed that, or felt that electrons were acting like waves. All right. So because of some of the experiments they were doing, electrons were acting like waves. It wasn't they were particles, because we know that they were particles from Thomson. If you recall Thomson, right, and the paddle wheel. Remember that when those electrons moved the paddle wheel. But there were some experiments that were showing that, wait, electrons not only are acting like particles, but they're acting like waves. And so with what de Broglie did was further model Bohr's model and say that, you know what, these electrons are kind of locked in to these levels. They can't go anywhere in between. And that's, again, what Bohr said. And so last but not least, probably the idea that this was really a true statement with electrons acting like waves and particles is they interfered with each other. Now, when I'm talking about waves, we haven't done anything with electromagnetic waves, but you've seen maybe a wave like this, right? Okay, and we have the distance from here is a wavelength, right? And how many times it goes by one point is a frequency. But what this interference with each other So when they interfere, you can imagine another wave going like this, kind of opposite, and that would affect them. Okay? Or if, let's say, we had this point right here, and we had a wave coming along, the wave would actually be diffracted by this solid thing. So there were some experiments that showed that electrons were like waves, but they're also like particles. And I've got one AP chemistry teacher that I know calls them a wavicle, which I think is kind of a clever way of saying it. So this is some real theoretical stuff, which is really beyond what we're going to be doing. But I want you to understand kind of the history behind what's going on with our atom. We had Thomson discovering electrons, Rutherford discovering the nucleus, then Rutherford's model right here, okay, then Bohr's model right here, and then de Broglie came in and said, you know, they're like waves. And so that's leading us to some interesting ideas about what's going on with the electron around the atom. And so basically the idea is that electrons reside in these areas we call orbitals. All right. Now, if we go back to this picture right here, again, these are energy levels, right? And I know this is kind of weird stuff, so you're just gonna have to bear with me. It'll make sense a little later. But these energy levels, energy level 1, energy level 2, energy level 3, those are, we're gonna end up calling those, at least those areas with a certain amount of energy, orbitals. And you can think of orbitals as kind of like the place for electrons. Okay, it's where the electrons hang out, and it's a really important concept, and it's something that chemists know to be true. Oops, boy, I hate when I do that. The thing that we know about orbitals that are important is they tend to take the idea of both the particle and the wave properties. So it's a model that supports both what we believe as far as electrons acting like a particle and electrons acting like a wave. So if you can imagine a nucleus, okay, we could have an orbital around the nucleus where maybe we could put a couple electrons, right? And then a bigger orbital, again, just an area where electrons reside, can hold a few more electrons. All right, and that's kind of our model today. Now, how they calculate this stuff takes some hardcore math, some three-dimensional calculus, wave function stuff, and stuff that's way beyond us. But the best way to think of an orbital, as far as a real-life example, is that we don't know where an electron is, because imagine an electron going around a nucleus. I'm just going to say we've got one, right? It's going around a nucleus, and I can only draw a two-dimensional space here, but it's going around super fast, right? And in all different directions three-dimensionally, all right? So you can't really see it, but if you were to look at it, it would look like maybe this shape, this sphere, or this other shape I'm going to show you in just a second. And so if you think about a fan that's spinning, you know there are three blades, at least usually, right? But when you look at a fan, right, there's a point here, all you see is this kind of solid thing right here, right? If you can imagine a fan there and it's blowing air, right? It looks solid to us. So the same kind of thing. So it's important that you understand that these orbitals are areas where electrons reside. Now I'm going to show you these shapes I just talked about. Understand that these shapes are not like hard walls in an atom. They are just areas where chemists and physicists believe the electron could be found. They're areas of probability. And they are some funny shapes, and they've been calculated mathematically. And the idea is that we're not really worried about how they got the shapes. We're just trying to understand that those electrons are going to be there. So here is a model of the orbitals, at least for the first three set of orbitals. Right now, the first one, the lowest energy orbital, is an s orbital, and you can see we're trying to draw three-dimensional here. We've got x. You guys know the x-axis and the y-axis, and there's our z-axis. Although I would probably rather make this y here x, and then going in and out of the paper would be z. Okay, but the first orbital is an s, and how I remember the s orbital is the first one. It looks like a sphere. Well, sphere starts with S, right? Okay, so then our next higher level of orbitals, and when I say higher level, I'm talking about higher in energy. So let's imagine this first line is an s orbital, and let's imagine this second one, and this is a real simplistic view. This would be the p orbitals. Okay, so p orbitals look like this, and I remember p by peanut shape. Okay. So again, it works for me, but it just reminds me of a piece. Some people call it the dumbbell shape. In fact, that's what this model calls it. But for me, P equals peanut. So the next higher level of orbitals are P. Now let's say we go to the third energy of orbitals, right? Oops. Let's say we're talking about this one right here. Now we're talking about the d orbitals. And that's what these 5 shapes are. Okay? And here we go. Here's a Richardson remembering technique. It looks like 2 dumbbells together, right? So I call it a double peanut. Double peanut for D. Again, use what you got to do, but I never forget it. Double peanut. So it looks like a clover, right? Except for this weird one. Look at this thing. This thing's along the z-axis. Now, I know this is weird looking stuff. The thing to remember is these are just areas where we believe the electrons would be if we were looking for them. It's not a hard shell. Okay, it's a high area of probability. And I'll talk a little bit more about that in class. But the idea is, let's say I have an atom with a bunch of electrons. If I put all of those d orbitals together, what do I get? Well, you've no doubt heard this term. I get what's called an electron cloud. So if I were to look at the atom completely, it would be completely, ooh, you know what? I think I could do this. I can put a little bit of gradient here. Let's see if this will work. Will it work? Nope, I can't get it to work. Darn it. Well, anyway. Oh, nope. So I'm just going to try and draw it in a little bit. So I would get this whole area around the nucleus would be, again, looking kind of like the fan. It would look like a solid thing, even though we know there are just a number of electrons traveling around the nucleus very fast. So you put them all together, you get an electron cloud. Now that is as deep as I need you to get as far as your understanding. Understanding that electrons reside in orbitals, as we have right up here. Electrons reside in orbitals, and that these orbitals have certain shapes dependent upon their energy. And again, that's all we're going to do it, because what we're going to do next is electron configuration. So I imagine there's going to be a number of questions you can ask me in the morning about this stuff, and I'll be glad to answer them. But hopefully this kind of made a little sense.